Hi, this is OrgoChemSimplified, and today we're doing a mechanism problem. We're asked, how do we go from this compound here to this compound here? So here we have an ester group, and that's transformed into a sort of beta relationship between two ketones. Of course, this is the enolate form, but it's just another form of a ketone. Okay, so let's see what we have here. We have a methoxide group, MEO minus, and methanol, the conjugate base, or the conjugate acid. Okay, so before I go into this problem, I want to preface it by saying this is a very challenging problem. So only try to attempt this problem once you've mastered the other problems. Okay, so our MEO minus, that's going to be the reactive species because it's more reactive than MEOH due to the deprotonation. So what is MEO minus? That's a methoxide group, and a methoxide group can act as either a base or a nucleophile. Well, are there any basic atoms here? Not really, right? Because the most basic proton is going to be one that is an alpha carbon to a ketone, or a carbonyl. But the alpha carbon here has no hydrogens. So there are no acidic protons in this molecule. That tells you that the methoxide group will act as a nucleophile, right? And what's the most electrophilic atom in this molecule? It's that carbonyl carbon. So what's the first thing that happens? First thing that happens is we have a methoxide, and that's going to attack the carbonyl carbon and form the tetrahedral intermediate. So what do we get when we form this? Get a ring, O minus, MEO. Okay? And so whenever we get the tetrahedral intermediate, what happens? The negative charge collapses and it kicks out another group. So you have two choices here. You can either kick out this oxygen or you can kick out the MEO, the methoxide group. What happens when we kick out the methoxide group? Well, we're just going backwards. So the only choice really is this oxygen right here. So that oxygen gets kicked out. We'll draw the next structure. Sorry, that should be a double bond right there. Okay, so we'll draw the next structure. The O minus comes out. We form this compound. Okay, so now what do we have? We have something like an enolate ion, right? We have a double bond and an O minus, right? So that's like an enolate. And an enolate can either tautomerize, so this double bond can grab a proton and form a keto form, or this can be a nucleophilic carbon. So if this is a nucleophilic carbon, what's the most electrophilic atom in this molecule? Well, it's just this carbonyl carbon, right? But what happens if we attack that carbonyl carbon? We get a 1, 2, 3, 4-membered ring, right? What do we know about 4-membered rings? They're not stable. 6-membered rings are stable, right? So the only choice that we have is for this to form a keto form. So tautomerization, this is going to grab a proton. What's the most acidic molecule? It's just the methanol. Okay. And so now we've formed this molecule here. Okay, this is not attached, so it's not part of the ring. That carbon is not part of the ring. Okay, and so now what's going to happen? Well, we have a keto form, so we'll form an enolate because this hydrogen is now acidic. Right? So you take your base, deprotonate that hydrogen, and we'll form the enolate. Right, so now that we formed the enolate, now this carbon here is nucleophilic because it's an enolate, right? So now this carbon can attack the carbonyl carbon, right? And what numbered ring do we get from that? We get a 1, 2, 3, 4, 5, 6 membered rings, and now it's stable. So what we did was we went from the negative charge being on this carbon to being on that carbon by going through 2 tautomerizations, right? And so now when we do that, we can form a 6-membered ring. And we can attack the carbonyl carbon. This right there, and we get a tetrahedral intermediate here, and now what will happen? Now that we have this tetrahedral intermediate, we know negative charge comes down. We have 2 carbons here, so those can't get eliminated. So the only thing that can get eliminated is the methoxy group. Okay, now we're almost at our product, right? So what's the difference between this and that? This is just an enolate form of that keto form. So we're just going to tautomerize it by removing a proton. So we take our base, deprotonate that proton, and form the enolate. And there's the product that we wanted. So as you can see, this is a pretty long, complicated problem, but what you want to do is you just want to follow all the steps. You know all the steps to solve this problem. You just have to work through it based on the tendencies of each of the individual intermediates, right? So we started with a methoxide ion. We knew it had to act as a nucleophile base. We knew that this molecule, our starting material, was not acidic, so it had to act as a nucleophile. We formed the tetrahedral intermediate. We determined that we had to eliminate this oxygen because if we eliminated the methoxy group, it would just have gone backwards, right? Now we got an enolate ion. our enolate ion, the carbon would have formed a 4-membered ring, so that was not stable, so we had to go through tautomerizations so that now this carbon could attack. This carbon was nucleophilic, and that carbon forms a 6-membered ring, which is more stable. Now we have the tetrahedral intermediate. It collapsed, eliminated the methoxy group, and after tautomerization, we arrived at our answer. So it's a bit of a complicated problem, but just try to work through the steps. If you know how each of the species reacts generally, or what type of species each chemical compound is, then you can work through the problem and you can arrive at the answer. So again, it's pretty complicated, but you can do it. And thanks for watching. I hope it helped, and if it did, try to spread the video to as many people as you can. Thanks.